Hi, welcome to my talk. Thank you for clicking play. I'm Ryan Williams, and I'm going to be talking about constructive separations in complexity theory. This is joint work with Lijie Chen, Chen, and Rahul Santhanam. So this talk will be about the problem of proving complexity lower bounds. And probably the one fact we know very well about lower bounds is that they are hard to prove. We don't know a great deal of them, but we know they're going to be hard. So, and the reason why there is because there are many barriers. Just to give like the three most prominent barriers discussed in the literature, there's relativization, there's natural properties, and there's algebraization. Okay, there are others, but these are the most commonly known ones. The high-level summary of these efforts show that the standard methods we use to reason about generic computation simply cannot resolve P different from NP, but can't resolve P different from P space, X different from ZBP, and X not equal BBP, a whole host of problems. There's a huge frontier of problems we cannot resolve using standard methods that we know. All right. So we apparently know a lot about what strong lower bounds cannot look like. We know many limitations on how such proofs must proceed. So the starting point of our work is the simple question, what could a proof of P different from NP look like? Right? Like we know a lot about what it can't look like and a bunch of other problems. We know what their proofs can't look like. Can we identify properties that such lower bound proofs must possess? Instead of barriers to strong lower bounds, can we identify obligations that strong lower bounds have got to obey? Right? Another way of thinking about it is we know how to prove a bunch of lower bounds. Okay, there are evidently lower bounds proved in this conference. Okay, there are a lot of lower bounds we know how to prove. So there's a gap, right? So the question is, what properties are missing from lower bounds we know how to prove, which we're going to have to include in a proof of a result like NX different from BBP or any of the other above separation problems? What are the missing ingredients in our lower bound toolkit? All right. So we'll discuss a potential answer here, which has an interesting way of connecting algorithms to lower bound questions. All right, so get a handle on this question. Let's look carefully at what it means to prove a lower bound. Okay, so let f be a function from bit strings to bit, and let fancy a be a class of algorithms. Okay, so a lower bound that f is not in this a is a claim of the following form. For every algorithm in that class, there are infinitely many n, and there are bad inputs x sub a of length n, so that the algorithm a differs from f on that input x sub a. Okay, so for every a, someone has to respond with a bad input x sub a that confounds a. In fact, we should construct infinitely many such bad x sub a's, because if there were only finitely many, they could be hard-coded into a larger but still finite algorithm. All right. So this is a way to think about the lower bound problem. I mean, this is literally the lower bound problem. So what we're looking at is fix a lower bound problem that we'd like to prove, and fix a particular algorithm A we'd like to prove doesn't compute F. What is the complexity of constructing bad inputs x sub a of length n? Right, so the lengths n are increasing. What is the complexity of this problem? We know if the lower bound holds, the bad inputs exist. How difficult is it to construct them? Right. So the literature on lower bounds gives roughly two types of answers to this question. Okay, depending on how the lower bound is proved. The first type is to choose a random input or do some counting argument to argue that a bad input exists. Right. So these typically rely on information theoretic type arguments. There are many, many examples. I'd say most proofs of lower bounds in, say, query complexity or communication complexity have this flavor. Various proofs of time-space lower bounds for explicit problems in P work like this. So that's the first type. The second type of answer is that there are efficient ways of choosing the bad input. And as far as I know, these almost always, if not always, come from diagonalization-based arguments. So to give a canonical example of this, the standard proof by diagonalization that the halting problem is undecidable is actually a constructive one. So given the code of a Turing machine that claims to solve the halting problem, you can efficiently produce a bad input in which this program fails to correctly decide halting. All right. So there's sort of two different ways of constructing bad inputs here. And I would say the first one is much more common nowadays in lower bounds work than the second one. All right. So a beautiful paper of Gutfreund, Schaltiel, and Toshma is our starting point here. So they showed that if P is different from NP, then bad inputs to SAT algorithms can be efficiently constructed. So I would guess that most FOCS attendees haven't read this paper before. Maybe the result even sounds a bit weird, but I actually think it's important and the proof is very beautiful, so please go read it, okay, if you haven't. I can't cover it here. So the following theorem can be derived from their paper. It says for every polynomial time algorithm, A, so let's say it takes n to the k time, there's another algorithm, R sub A, that for implementing n, R sub A on the string of n1s outputs a formula f sub n of length n, so that this f sub n is satisfiable, but the algorithm reports unsatisfiable. Okay. Furthermore, this refuter algorithm runs in also polynomial time, but a larger polynomial. Okay. So yeah, this algorithm R sub A is a refuter in the terminology of cabinets who studied de-randomization with respect to polynomial time refuters in various contexts. So we're saying that if SAT is not in P, then for every polynomial time algorithm, there's another polynomial time algorithm which can refute it, which given the string of n1s can just print counterexamples for that algorithm. All right. All right. So let's generalize this. Let's make a definition. So for in general, let's say there's a P constructive separation that a function f is not in a class of algorithms A. If for all of the A algorithms, there's a polynomial time algorithm R sub A, which for implementing n, given the string of n1s, can output this bad input that sort of shows that the algorithm A doesn't compute the function. All right. Then restating the theorem of GST, we get that if P is different from NP, there is a P constructive separation that SAT is not in P. So in other words, SAT is not in P if and only if there's a P constructive separation that SAT is not in P. Right. So P constructivity is inherent in a proof of P different from NP. Okay. So, okay, so this is saying that if P is in from NP, there's a constructive separation of that. So the question is, which lower bound problems require these kinds of constructive separations and which do not? So which lower bound problems sort of guarantee, just from the statement of the lower bound, that there must be a constructive way of producing bad inputs, and which lower bound problems don't have this property? Okay. So note that this is an algorithmic question about the nature of the lower bound involved. So we're like, when we say a lower bound is P constructive, we're claiming the existence of an algorithm that solves a certain problem, namely the search problem of finding this bad input. So we're asking what algorithms are being applied by these lower bounds, these complexity class separations. Okay. So in this paper, we argue that constructive separations are going to be a big key to proving major separations between complexity classes. Somehow they're like a missing link. We're not saying we know how to prove them. We're not saying we know how to get them. We're just identifying this property of various lower bounds, which seems extremely important. And it seems it's like a dividing line between lower bounds we know how to prove and lower bounds that seem far away. Okay. So the first kind of results we show are that essentially all open separation problems regarding polynomial time require constructive separations. Okay. So the formal theorem is that for all complexity classes C, which could be P could be ZPP, zero error probabilistic polynomial time, or randomized polynomial time, BPP. And for all D, which are a host of different classes that we believe are different from these polynomial time classes, if C is different from D, then there is a C constructive separation that C is different from D. Now, I can't define BBB constructive here or ZBB constructive, but there is a natural way to do that, okay? So what we're saying is that, like, essentially all these problems around polynomial time are going to imply constructive separation. So if we manage to prove a good separation against polynomial time, we're going to get a constructive one also, whether we like it or not. So I guess we might as well think about the algorithmic problem of getting a constructive separation. Okay, the second set of results says, okay, there's many lower bounds that we know very well. If we could make them constructive, that would also require resolving major lower bound problems. Okay, so the second set of results shows how much more powerful constructivity is compared to other methods. If we could make known lower bounds constructive, then we'd already be resolving major open problems in circuit complexity. Okay, so to give one example of this, there's an old result of MOS from the 80s that says that recognizing palindromes cannot be done by one tape non-deterministic Turing machines running in little o of n squared time. Okay, it's a classic argument. You can be recast in terms of non-deterministic communication complexity, counting arguments, what have you. We show that if this lower bound could be made P constructive, then in fact you get an amazing consequence. You get that exponential time contains functions of exponential size circuit complexity. And by in Polyazzo-Wigderson, this would imply things like P equals BBP. So constructivizing this lower bound, making it P constructive, would in fact imply universal de-randomization. Okay, and we actually prove a much more general statement than this example one. Okay, you can see the paper. Let me demonstrate a couple more examples along these lines. So the second example is that of randomized streaming algorithms. So many problems, including very simple ones, are well known to have essentially linear space randomized streaming algorithms. Like they require linear space for a streaming algorithm to solve. So another theorem we show is that take any problem in NP whatsoever. Okay, if you can get like even P to the NP constructive separation. So you have a polynomial time algorithm is a SAT oracle that can find bad inputs for a low space randomized streaming algorithm. Okay, if you can do that, then you would get another major open problem separation. You'd get X to the NP is not equal to BBP. And this is one of those embarrassing open problems in complexity theory, but nevertheless, it is a long-standing open problem. And so getting even kind of mildly constructive separations for randomized streaming algorithms would be a major consequence of complexity theory. So for a third example, randomized query lower bounds. So we even making some of these like very basic lower bounds constructive would have big consequences. So consider promise majority, or also known as the coin problem, where we want to distinguish bit strings that have greater than half plus epsilon fraction of ones from strings with less than half minus epsilon fraction of ones, where epsilon is some parameter greater than 0. Okay, and this problem is well known to require sort of theta 1 over epsilon squared queries. Okay, it's well known to require this. So we show that if you could get a constructive separation for this against randomized query algorithms, then you get a major consequence. So promise majority is actually has low circuit complexity. It's in uniform AC0. Okay, so what we show is that if there were a uniform AC0 constructive separation of this coin problem from randomized query algorithms that use, these randomized query algorithms use too few queries and poly 1 over epsilon time. If you could get a constructive separation for this query lower bound, you would in fact prove P different from NP. Okay, so in uniform AC0, you can solve the promise majority problem. And now we're asking, like, can uniform AC0 also generate bad inputs for fixed randomized query algorithms? If they could, then P is different from NP. Okay, seems like a pretty wild consequence of just making a basic randomized query lower bound constructive. There are many more examples in the paper. So I want to conclude with some open questions. These are kind of the biggest ones I can think of, but there are more in the paper. So the first one is that over 40 years ago, relativization said that direct diagonalization-based proof methods are limited, right? So like the time hierarchy theorem, the direct diagonalization type proof methods are limited due to oracle results. But we also know that any major separation against P is going to require a key property of diagonalization-based proofs, namely this constructivity, this ability to efficiently produce bad inputs. So the big question to me is, what other methods of proof could yield this kind of consequence, the ability to produce bad inputs? This is something I think should be studied very carefully. Another thing about our results is that you might have noticed that it's only for polynomial time, randomized polynomial time. So what about separations against log space or NC or ACC0? Does NP different from log space imply a log space constructive separation? Things like this. I'm not sure. It's a good question. So the last question is, so we showed that if you get constructive separations for lower bounds based on the probabilistic method, okay, then you would get de-randomization results, right? You would get these circuit complexity lower bounds that imply de-randomization. So what I'm wondering is, maybe there's a implication in the opposite direction. Maybe there's an equivalence, okay? So I'm wondering, like, maybe constructivizing known lower bounds, like that are proved by counting arguments, maybe this is a de-randomization problem in disguise and is actually equivalent. I don't know. That's all I got to say. Thank you very much.